the ECP effort that we have for OpenMP, and is part of a project called SOLVE, that the goal is to advance OpenMP standard as well as the implementation of OpenMP in the LLVM compilers. So for today, I want to give you a very brief overview of where we are in terms of OpenMP, what we have in the latest standard, and where we want to go in the future. But before we talk about the future, I just want to talk about what we currently have in OpenMP, which is OpenMP 4.5, which was released at Supercomputing in 2015. And in this specification, we have many refinements in OpenMP to improve the support for accelerators in terms of the device support that we have in OpenMP. As of now, we also have new features to improve new types of parallelism in terms of that were not previously supported. For example, we have support for do-across and task loops, which are going to be very helpful to support types of parallelisms like wavefront parallelizations or loopness that we want to execute within a tasks. In addition to that, we also have more clarifications that were not very clear in 4.0 and minor enhancements in different features for OpenMP, like, for example, support for C++ array reductions and other new capabilities that we have for the tasking support in OpenMP, like the support of task cancellation, as well as a better way to specify thread affinity in OpenMP 4.5. One of the substantial improvements, as I mentioned before, is that we have enhanced significantly the support of the target directive in OpenMP 4.5, so that we can more easily program accelerators. And this is a list of new features that we have in OpenMP 4.5, which we'll be covering in the second part of this webinar. And this is just a list, so for you to become familiar with the topics, and we're going to explain how to use them, as well as how this can help adapt better your applications to use accelerators with OpenMP. In addition, we have other refinements in OpenMP, like, for example, clarifications on how to use the SIMD directive, like, for example, how we can specify a chunk of iterations that we want to execute in parallel in terms of vectorization. We also have clarifications on how to specify thread affinity by defining a new grammar on how we want to abstract the architecture where the threads are going to be mapped. And that grammar is part of what we call OpenMP places, which is how we define and abstract a machine to OpenMP, or the different execution of threads. And as well as we have a better support for logs and critical sections by passing hints to the runtime and the implementations on how we want to implement them, as there are different strategies that can be used for that. And as we are committed in OpenMP to improve the support for Fortran, we are getting very close to support a complete support of Fortran 2003. There are still some limitations, but we plan to address them in OpenMP 5.0, which is basically the next release. In addition to that, we have other minor improvements. As I mentioned before, we can support now priorities in the tasks, as well as some improvements in terms of the support of C++, like we can now support reference types in the different clauses, and we have now rules on how we're handling those. There is also a list of in the OpenMP organization website, which is openmp.org, we keep a list of compiler support, which basically describes the status of the implementations across multiple compilers, and which ones are available, and so that you can start testing them or giving us feedback on how you're using OpenMP 4.5. So one of the things that we are focusing now is working toward the next release of OpenMP, which is going to be OpenMP 5.0. And before that release, we had been releasing technical reports that to give the community a little bit of a preview of what we want to add to OpenMP 5.0, with the idea that these extensions are going to be changing and evolving over time until we get the release in OpenMP 5.0. And part of these extensions include functionalities such as reductions for tasks and task loops, which is a feature that is very important and users have requested that. In addition to that, we want to keep improving the usability of OpenMP on how we program accelerators by reducing the verbosity when we have declared target routines that are referenced inside target regions. We want to basically, if a subroutine is referred inside, it is called within an accelerator, we want to have already a version of it available for the accelerator without the user to declare it as such. So this is, for example, this is one of the changes that we want to add to improve the usability of OpenMP for accelerators. In addition to that, we want to improve the support of the accelerators for C++, as well as add other types of synchronizations and that we would like to see to improve how we synchronize tasks. For example, we will have support for task wait with a depend clause to be able to satisfy dependencies better and improve the synchronization points in OpenMP. So what are we going to be seeing in OpenMP 5.0? Right now, we just have like the main topics that are kind of driving the standard, and the topics that we want to address in OpenMP 5.0 are related to memory locality, affinity, and how to manage complex memory hierarchies. And for that, we just released a technical report this year that describes an API to manage different types of memories with OpenMP. And this is something that we really need feedback from the community so that we improve the way we specify this in the standard. And this is something that we're going to start talking a little bit more as we progress the way we are defining it. We also keep in mind that we want to support better the standards in terms of C++ and Fortran and have full support for Fortran 2003. And then keep improving the way we are supporting accelerators in OpenMP. And one of the challenges right now in the way we specify OpenMP for accelerators is the way we map variables. And we want to improve the way we can map complex data structures to the accelerator and solve a problem called deep copy. And this is something that we are committed that we want to solve in OpenMP 5.0, as well as improve the way we can program multiple devices by providing higher level constructs that will help us to do that. We also want to improve the way we interoperate with other threads that are not attached to parallel regions, as well as improve the way we specify dependencies and so on in OpenMP tasks. The other feature that we want to add and work further is the way we do debugging in OpenMP, and we have a way right now, the OMPD debugging interface that we're developing, and this is something that we really want to focus on. OpenMP 5.0 is scheduled to be released by Supercomputing 2018, and but before we do that, we plan to release another technical report by Supercomputing 2017 that will give an update on where we are in terms of OpenMP 5.0 and what new features are going to be seen. So for people that are developing codes in OpenMP and they find currently a limitation in OpenMP 4.5, it is really recommended for them to look at these technical reports just to see if this issue that they have or extension that they want to see is already described in one of these technical reports. These technical reports are available in the OpenMP website, which is openmp.org. Okay, so that's kind of like a very to give you a very brief overview of where we are. So we will now start the second part of the webinar, and if there is any questions at this stage, just let me know. If not, we can go ahead and start the second part, which is meant to explain a little bit better how OpenMP target works and how we can map the data structures better with OpenMP 4.5 to the accelerator. So I just open the room for questions for the moment. If not, I will just proceed.
If anybody has any questions, you can unmute yourself or you can type it in chat. In the meantime, Oscar, if you want to go ahead and bring up the next presentation.
Okay. All right. So this next presentation is basically to explain and give you a little bit of an overview of how we can use OpenMP to program accelerators. Since OpenMP 4.0, OpenMP supports heterogeneous systems, and the way we support it is that we support it through an accelerator model where we can have a host device that can be a CPU multi-core system, where we can have one or n number of accelerators, and OpenMP provides the different kinds of directives to program them. In terms of OpenMP, a device or an accelerator is an implementation-defined execution unit that has its own local storage, and the host or the initial device is responsible for manage that device by creating and destroying a data environment in the device, mapping variables to the device, offloading work to the accelerator or the target device, and also do any sort of updates between the data that is in the device and in the host. So the model is very host-centric, and the device acts as as an accelerator, the target devices. There are different clauses in OpenMP 4.5 that we can use to program the accelerator. This is just to give you an overview of what they are. We have a target clause where anything that is inside the target is going to be code that's going to be executed in the accelerator. We have clauses to manage the device data environment and also map variables and update the variables between the host and the device. And for those, we have OMP target data, target enter-exit data, and target update, and as well as declare target. All of these directives are meant to control the data environment, and we're going to discuss them, how to use them more in depth further on through the webinar. In addition to that, OpenMP 4 and 4.5 provides new mechanisms to express other types of parallelisms that are available in the device or the accelerators, and such as OMP teams and OMP distribute, which is basically a way to share work across teams that we create in the accelerator or the devices. This is a very important type of parallelism because it's what, for example, is supported on devices like GPUs. On the other hand, we also have runtime support where we have a set of APIs and run to control the default devices and get information about the number of teams and who is the initial device and so on, and as well as other environmental variables to control things like the thread limit, that, for example, how many threads we want to have per team, for example, the maximum number of threads. Just to give you a very brief overview, this is just an example of how we can use OpenMP for accelerators, where we have an original, let's say, a typical OpenMP 3.1 code where we have a OMP parallel do, and we can basically enclose that region with the target directive, and that will automatically place that code into the accelerator, which basically will generate the code that will execute in the accelerator, as well as create the data environment that we need to do that for the code. When a host encounters a target, when a thread in the host encounters a target directive, it transfers control from the host, the target device, and as well as it maps its variables that we want to either create in the device or map to or from the device. And so the host thread can either wait until the target region completes, or it can continue the execution depending on if you specify asynchronous execution for the target region using the no wait clause. So we have an initial thread in the host, and when it encounters a target region, what it does is that it creates a completely new OpenMP environment in the accelerator, where the accelerator gets initialized, and in this new OpenMP environment in the accelerator, we start with one thread, and that's basically an initial thread, and then we start creating the data environment by allocating and mapping the variables that we specified that we want to map from the host. So in this case, we will allocate, for example, the variables and also copy the values that they have in the host to the device. So when that happens, the thread starts executing in the device, and then it encounters, all the different types of parallelism that we support inside the target regions. Like in this case, it will be a parallel do, where we will have multiple threads that are going to be spawned, and then at the end, we're going to, for example, synchronize them with the implicit barrier that we have in parallel do. And then at the end, when we finish executing the code, we can copy out the values of the variables that are with the map type from, and basically deallocate the data structures that we allocated on the device. So that's like in a nutshell how the accelerator model works in OpenMP, and there are different variants on how we can do this, and that we're going to discuss later on. But the key concepts is like we have to think that the target clause creates a completely new OpenMP environment in the accelerator. One of the things that is very important is the concept of data environments, and OpenMP supports multiple accelerators as well and it can create data environments on the different accelerators and map variables across them. And this is important to know because once there is a data environment in the accelerator, you can map variables, which are basically an original variable in the host that has a corresponding variable in the device environment. And these variables are meant to be synchronized within each other throughout the execution of the program between the host and the device. And there are different directives to do that, and to either basically allocate them as well as copy to or from the values from the device. One thing that is very important in OpenMP is for accelerators is like we're specifying new types of parallelisms. Initially, for example, in OpenMP 3.1, we have concepts of nested parallelism and so on. In OpenMP 4 and 4.5, we have new concepts for spawning threads. And one of these new concepts is the addition of a clause called OMP teams, which basically can help to create n teams of size 1 or of one thread each in the accelerator. And the idea here is that when we create all these n teams, and each team will have one thread, and these threads, they cannot synchronize within each other. So that's one of the restrictions of this type of parallelism. And then within each team, a team can call, for example, a parallel region, and then it can spawn threads that belong to the same team. So these threads that belong to the same team, they can synchronize with each other. So like, for example, they can call locks or critical regions and so on. And what we call in OpenMP 4 and 4.5 is like all the threads that they can synchronize with each other, they belong to the same contention group. And the different teams belong to different contention groups. And this is important because this is the type of parallelism that some devices on other devices don't support in terms of, but the OpenMP provides an abstraction such that we can still specify it and run it on multiple devices. But the implementation may define on how we define these teams, or how many teams we create at runtime, for example, if the user doesn't specify a number of teams that we create at the runtime. It is important that when you write performance portable code to be able to use this type of parallelism so that a code can run efficiently in a GPU as well as on a multi-core or a Xeon Phi architecture. As I mentioned before, we have the teams construct that creates a league of thread of teams, and basically the user has the option of specifying how many teams you want to create, although the implementation is also can pick up to that number. And then if a team calls a parallel region or creates more threads, there is also a clause in the OpenMP teams that can limit how many threads, what's the maximum number of threads a team can spawn. And this is just an upper limit that if you specify that, that constrains until how many threads we can create within a team. So as I mentioned before, teams cannot synchronize within each other, and teams can only be called when they are nested inside a target region. So basically, if you define an OpenMP target and you want to use OMP teams, you have to make sure that teams is called after the target, and there is no statements in between. There is also other restrictions that we have in OpenMP teams as what kind of OpenMP constructs we can embed or nest inside. So for example, these are the constructs that we can nest. For example, we can do a distribute, and this is meant to be a directive to distribute work between the across the different teams, or we can spawn more threads or create a work sharing directive like parallel 4 with and spawn more threads as well, or call a parallel sections region. So as I mentioned before, we can use the OpenMP teams after the OpenMP target, inside the OpenMP target, and then that creates a number of teams and with one thread, and then we can have a directive here called OMP distribute, which is basically a directive that can help us to work share work across the teams. So in this case, the work is of a loop that we have here can be distributed across the teams, and which will be consisting of one thread each team. And the restriction here is like there is no these iterations, they cannot synchronize across threads, across teams, and there is no barrier at the end of a OMP distribute construct, and we can specify a type of scheduling that we have with a chunk size, and this schedule is static. So one thing before we move to the second part of the webinar is just to remind you that if you want to write OpenMP portable code in your accelerator, you need to be able to describe all these different types of parallelisms available in OpenMP target. So basically, just a very typical example would be that if I have a nested loop and I can use one of the combined directives in OpenMP inside the target region where I can define parallelism at the level of the teams or the threads within the teams, and as well as parallelism if the architecture support SIMD, for example, or vectorization or SIMD type of parallelism. If you do that, if you specify the parallelism of this code this way, you're kind of like guaranteeing that no matter what device you encounter, the implementation or the runtime can pick the correct values or the schedules that we want to have, and it can run efficiently on different architectures, or we can use this to write performance portable code. What happens in here is that if we just write OpenMP this way, there are a lot of implementation defined values that the runtime and the compiler will pick, like for example, what's the number of teams, the chunks in the distribute schedule, the thread limit, the loop schedule for the parallel 4, or the SIMD length that we want to specify. And for example, in one architecture, for example, a compiler or runtime may choose to just use one team and then have all the parallelism at the parallel 4 and SIMD level. Or in other architectures, we'll focus on having more parallelism by spawning more teams and threads, and that will run better in an architecture like a GPU. Okay, so this second part is part where Tom Scogland is going to be presenting, and we're going to go a little bit more in depth in the OpenMP 4.5 or 4 for accelerators, specifically on how you can map variables to and from the accelerator to the host, and how we can specify that efficiently with the new OpenMP 4.5 constructs. So with that, I pass the presentation to Tom.
I'm going to go over a few different features of OpenMP 4.5 in a little bit more depth. specifically around target features, target directives, and data sharing. Some of the ones named here I'm not going to touch on too deeply, but at least give an overview of how some of the constructs that Oscar gave an introduction to can be used, and also where some of the common pitfalls are for early users. First is updates. Now, or rather updates to data mapping. So in OpenMP 4.0, we added the map construct by which you can allocate, create a view to the device, from the device, or both directions for variables and array sections of pointers and arrays. The mapping semantics for OpenMP 4.0, while vaguely related to other models like OpenACC, did things a little bit differently in that they all include a presence check. All unlisted variables were mapped to from, and array sections were mapped in two parts. Device scalar storing the address of the device buffer, as well as a device buffer that would store the data. And the presence checks operated on the address of the list item, never the value. So pointers referenced in a region but not mapped would be mapped to from as a scalar. And as a result of these examples like this, where you have a target data map of an array and then attempt to use it on the following line without naming it, this actually is an error in OpenMP 4.0. So because it gives you a copy of the pointer value, you probably got a seg fault with that. And by the same token, even if you do everything correctly and you actually do name it across a call, you get the same problem because the address of the pointer will have changed in the call. Now, this is probably sounding a little bit nasty, and that's intentional. Again, now you're actually mapping array across the call. This works. Unstructured maps give us the additional functionality to not have to have our data scoped. Okay? The target data construct, as noted on the last few slides, has to surround something. For example, here, the scope of the map data is only across the OMP target foo function. So the data is made available, allocated if necessary, deallocated if necessary, and all handled in the one construct. That works great for code that has this kind of scoping in it. But for code that may need to do things in separate scopes, like here if you want to write a wrapper function to map an array, you don't want that array to subsequently be freed when the function is ending. So instead of using target data, it uses target entered data to begin an unscoped region, which can then be ended in another code path somewhere later that has the same behavior across target regions in the interim. It changes it from a static to a dynamically scoped construct. Now this example uses the enter data to map the array as we did before, and then calls into another function, OMP4 target foo, which maps the same array in the same way. This example in OpenMP4 did not work. Now, why not? It's being mapped by the address of the local variable. That means map fails to find it because it's looking for the address of a non-existent stack variable. It gets mapped again, and the first mapping is lost. Now, a Fortran example of a similar thing would be this target data map. Notice that the array section syntax is frequently not necessary for Fortran, even for arrays, because the shape is known. We can come back to this potentially later. But the reason I went through some of these cases is the mapping in 4.5 can seem a little bit daunting, but it solves all of the problems that we just talked about from 4.0. And this is why many of the compilers are directly targeting 4.5 now, rather than going for 4 first. And the basis of this is, instead of having a single rule that covers all variable types, we decided to split it out. Scalar variables, meaning any kind of intrinsic basic type, int, double, float, char, etc., is considered scalar. They are first private by default, but they can be mapped explicitly if the first private behavior is not desired. Pointers and arrays are mapped as zero-length arrays, somewhat equivalent to the OpenACC present concept. By default, the value of the pointer is looked up, and if it is found to be present on the device, then the pointer is translated. If it is found not to be present, the pointer is set to null. For arrays, if the shape is known, the array gets mapped. Others, which would be aggregates like structs, classes, unions, are mapped to from by default. Now, the other change we made is that when mapping an array, presence checks are performed in the value of the pointer, and the scalar holding it is now first private. So there's only one mapped buffer on the device that, if allocation is necessary, gets allocated, such that we don't have a split between the pointer and the data anymore, which simplifies parts of the model. And now we avoid the problems that just came up with unstructured data. There are no more dead stack variables in the presence table. Well, unless it's explicitly requested, and, well, there's not much we can do about that. So this example that we went over before, unstructured map, target entered data, map to R, map to from R in the other function, is now working correctly. And in point of fact, as of OpenMP 4.5, the extra map to from on len here with array and length here is not actually necessary. It's found by default. The call example from before that also works. So the main point that we want to draw out here is some of the rules for mapping are a little bit complicated, especially in the defaults. Hopefully they'll be able to do what you want by default the majority of the time now. But whenever there are data-related issues, this is a place to look. Now, something else that we've been putting a lot of work into, Oscar mentioned earlier the issue of deep copy. Deep copy is an active area of discussion. It has been for quite a number of years because it's very complicated, and how we address it could have significant implications for kind of the expressibility of the language as well as what it looks like. Now, while this is not a full deep copy solution, we've recently accepted something that allows for manual deep copy, at least for basic structures, and we're referring to that as submapping in this section. So an example of this, and as of the most recent TR is something that you can do, is rather than having this say map to A, which would map the entire struct, or an entire copy of that struct, say. You don't want to be mapping huge unnecessary array unless you absolutely have to, right? So implementations are allowed to map only pieces of structures that are named where only those pieces are named. So in this case, the compiler would be allowed to generate a new struct on the device that only contains len and buff and use that as the mapping. The additional bit of syntax here is that a.buff with an array section means both map the array section itself and attach it to A, or a.buff rather, such that when A is used on the device, the buff pointer points to the device array appropriately. Now, at this point, before I go too much further, I probably should have done this a little bit earlier, but I'd like to see if anybody has any questions before we move on.
So, Tom, there has been lots of questions going on in chat. I don't know if anybody else wants to unmute themselves and ask a question. We'll pause for about 15 seconds and see if anybody wants to do that.
All right, that sounds good, thanks.
Just as a reminder, you can unmute yourself by clicking the microphone out the next or beside your name. But I think Hal's been doing a great job with the chat questions, Tom, if you want to continue on.
Very good, and thank you, Hal, by the way. All right, so target directives are the next topic in this section. And this is kind of to cover all the different variants that we have. Target enter data begins an unstructured data scope. This is something that I strongly recommend the use of. In fact, generally speaking, I find enter data and exit data to make for clearer code than the equivalent scoped constructs, especially in object-oriented languages like C++, where you may want to include mapping as part of construction or as part of methods inside of a class. These are fantastic for that purpose. And an example of that here is, say you want to write a custom vector class for yourself. When the constructor executes, allocates the data on the host inside a contained standard vector, say, you can use an enter data to allocate that same buffer on the device, or rather to make a view of it available, and in the destructor, get rid of it. This kind of pattern makes these unstructured data constructs especially helpful. Now, no wait is another one that is not widely supported yet, but we consider extremely important for performance going forward. And the effect of this is that all target regions are tasks as of OpenMP 4.5. So if you don't add the no wait clause to a target construct, absolutely nothing changes. The task is executed immediately, and in line with everything else, it's just a mechanism that allows dependencies to be expressed between asynchronous tasks on the host and asynchronous tasks on the device. Right, it will wait on dependencies. With no wait, the region is allowed to run asynchronously. This allows the use of, say, CUDA streams or OpenCL queues by the implementation. It can have interdependencies between asynchronous constructs. Copies and computation can actually proceed in parallel this way. The unstructured data constructs support no wait, as does target itself. And it allows you to do things like this, where, say, you have a computation made up of a number of tiles, and each of those tiles can be processed in parallel. It's unfortunate if you have to wait for the entire copying in of all the data to be able to start computing on the first tile, and likewise for all of the data to come back out before you can do subsequent processing on that tile, perhaps. By using no wait and depend in this case, the depend is actually on the tile itself. As with regular OpenMP tasks, depend takes a direction, in, out, or in, out, meaning whether the dependency is only inward, so other tasks with inward dependencies shouldn't wait on this one, or in the other cases, if other tasks should wait on this one. In this case, we want any previous dependencies on this tile to be waited for and any subsequent ones to wait on this construct. And rather than using, say, stream numbers, OpenMP uses the address of a piece of memory to indicate dependencies. So the first tile in this case, or the tile that is being worked on, is used as the dependency so that a subsequent tiled computation could actually interleave with this one if desired. And the effect of this is that the first tile can be, in queue, it's input, computation, and output, and while the first tile is computing, the second one can be copied in. This is very much like asynchronous programming in other kind of GPU models, but with the added benefit that in this model, if you want to have a CPU task that depends on data from the GPU or GPU tasks that depend on data from the CPU, it integrates fully with the CPU tasking mechanism. You can use the same depend clause, create an OpenMP task on the host, and have that become part of the whole graph of tasks, rather than having to manage a device and the host separately. Now, an attendant example in Fortran it works essentially the same way. The only difference is the spelling of the constructs. Right, now, this particular example has the advantage that it uses multiple kinds of depends. In this case, df1 is an output dependency of the first task, only an input dependency on the second task. So any subsequent tasks on df1 will not wait for this one. But atmpx1 is an output task, which causes the subsequent asynchronous update to wait, which then causes a host task to wait on that result such that it can print a result. Right. This is also an example of a host task interacting well with device tasks. Now, right, Post tasks in C and C++ will end up looking more like this. It's the same exact kind of thing we had before, except that now we have post-processing on the host that can use data that came back from the device. Now that covers the initial kind of high-level material that I wanted to go over. I have some more in-depth data management material for integration with native models. If we'd like to go over that. Oscar, would you like to touch on that, or should we continue to part 3?
First of all, let's ask everybody if they have any questions. We should, at this point, answer questions, especially for those who are interested in using OpenMP for accelerators, and they want to understand how to map data structures or basically map any variables, which is one of the most difficult things to express in OpenMP. And we want to use this occasion to clarify and provide as much material that we want to accomplish that, as well as understanding more what sort of data structures people are using in their codes and what sort of support we want to provide in terms of deep copy and so on.
Right.
So just as a reminder, you can ask a question by unmuting yourself. If you can't figure out how to do that, just let me know in chat and I'll be happy to unmute you. Oscar and Tom, I think you can, oh, we do have a question. So one of the questions we're being asked is how are data arrays that are part of a type in Fortran 2008 mapped?
Okay, so that's still partly under discussion. The standard base for OpenMP as of 4.5 is Fortran 2003. But the same question largely applies if you have user-defined data types. So, as I mentioned a little bit earlier, it's possible to map parts of substructures in C. It's possible to do the same thing with Fortran. So, as of right now, the way to make sure that those member arrays get mapped is to map the structure as a whole and then map array sections for the members that are arrays such that they get attached on the device. Some implementations do automatic deep copy for Fortran structures with arrays that are not marked allocatable. But generally speaking, they all require allocatable arrays to be explicitly mapped in that fashion.
Yes. So Tom presented some slides that shows, for example, how to map individual members of a data structure, and that's currently supported in OpenMP. And yeah, as one of the examples that we have. Are there any other questions before we move forward a little bit more in depth?
Hey, Oscar, I don't see any more questions, so if you guys want to continue, please do so.
Okay, so since we have a little bit of a few minutes, I will ask Tom if we can go a little bit deeper into how we deal with pointers in OpenMP for accelerators.
Great. Thank you, Oscar, and I will do that. So We touched on how mapping behaves, but one thing that tends to come up pretty frequently when we're talking about target directives is interoperability with native libraries, native code. This might be CUDA, it might be simply, say, native Knight's Corner, Knight's Landing code, it might be OpenCL, whatever it is, there is generally a desire for a way to reuse some of the kind of well-tested libraries like, say, Magma, cuFFT, cuSparse, that kind of thing. And so OpenMP 4.5 provides a way to get access to the underlying layers behind map, and also to take native pointers and make them usable with OpenMP. Now, we refer to this generally as pointer interoperability, but the actual constructs are referred to as useDevicePointer and isDevicePointer. useDevicePointer is on target data. This actually is a typo. The isDevicePointer is used on target. And the first allows you to get what we call the associated pointer, the host handle to the device memory portion of a mapped variable, to, say, pass it to a GPU-enabled MPI. isDevicePointer allows you to take an existing device pointer that you already have, or that you allocate through an OpenMP API that I will come to in a minute, and pass it into an OpenMP target region for use without having to separately map it. Now, one of the more popular examples of doing this is, say, that you've been working on, let's say, a CUDA platform that has a CUDA-enabled MPI that can directly take a CUDA pointer and send from the device without having to copy back to the host first. Now, you've been using OpenMP to actually write your code, so you've mapped your buffer, and now you want to send it from there rather than having to copy back to the host first. And by doing useDevicePointer, buffer actually gets first privatized across this scope, and its value is set to the appropriate CUDA pointer if you're using CUDA as a native platform. That way, MPI can send it from right where it is. Now, the other way is, let's say that you have a largely CUDA application and you want to write some routine in OpenMP. Now, I just have a simple sum here, but one example of something that I've heard people wanting to do with this is reductions, which are somewhat frustrating to write efficiently in CUDA from scratch, are relatively simple to write in OpenMP. And if you know that you're going to be taking in a CUDA pointer and you know that you have a CUDA-enabled runtime that is using CUDA for the target regions, then you can take a CUDA buffer pointer, pass it through isDevicePointer, and use it as normal. And in this case, you get your reduction. The compiler generates, well, hopefully, an efficient reduction for you rather than having to write that in manual CUDA. Now, the other part of this, and I mentioned this kind of as an aside earlier, is we've decided to expose some runtime API routines to allow the management of data manually with routines rather than just through directives. Let's see. Now, the first of these is OMP target alloc. This is basically just malloc, except that you can specify which device the memory should be allocated from. It returns a pointer that can be used with isDevicePointer, and thus is an appropriate native handle to a piece of device memory. By the same token, you can free that memory. Well, that shouldn't be size, it should be, well, the pointer. But say that you want to write that same sum that we had before, but have it be generic across all OpenMP targets. You can allocate the buffer with OMP target alloc, get the default device here to get the device number, and pass that in. isDevicePointer will always work with an OMP target alloc buffer. This is currently the only way to allocate memory on a device without having a corresponding buffer on the host. Now I'm going to break real quick. It looks like there's a question from a couple of slides ago on direct MPI sending. The answer in this case, well, so the question was, when sending data directly from the device using MPI, internally does a buffer in host memory become involved? And the answer in this case is MPI implementation dependent. OpenMP gives you a way to get the device pointer, and if you have a, say, CUDA-enabled MPI that can do GPU direct RDMA from the GPU to a NIC, it's entirely possible that it can be done without a host buffer, but it's entirely MPI dependent. And in fact, some even that have that capability stream through the host to reduce overall latency for small messages. It's implementation defined is usually the term used for this. Now, the rest is what we call OMP target associate. Associate is a little bit different from the rest of the API routines in that it's not a way to allocate memory, manage memory. This is a way to hook into the mapping system of the runtime that you're using. When given a host pointer, a device pointer, size, and the device number, it causes any reference to that host pointer to find that device pointer as present. There's a corresponding disassociate to remove these, and one note is they're both defined to invalidate the contents of the device buffer. But the main use of this is if you have a device buffer, say for CUDA, that you want to use with some OpenMP code, you've already got a host buffer, you can take that CUDA pointer, OpenCL, CLMem, what have you, and associate the two such that when working through the OpenMP code, it works just as though it had been mapped. Memory motion, also something we support. OMP target memcopy is a pretty much traditional memcopy interface with the caveat that, of course, it takes device numbers. It also takes offsets. This is because it's not necessarily safe to do pointer arithmetic on a device pointer. This is in response to certain backends, and this probably doesn't merit discussion here. If anybody has questions on it, I'll be happy to answer them. In addition to the traditional memcopy interface, we also have a rectangular memcopy. That's what we call it. This is a multi-dimensional copy that can be done in one operation. Main benefit to this is, say, you're running a problem that needs to transfer a subvolume from a matrix that is non-contiguous but is itself logically rectangular. That can be expressed in a single call here and allows some devices to take advantage of multidimensional direct memory access engines and similar things to provide much better transfer rates than are possible by doing it with multiple mem copies. And that covers what I was hoping to get through in part 2.
So are there any other questions?
Oscar, I don't see anything else in chat either, so if we want to move to part 3, we can do that.
Okay.
Sounds good. I'll transfer the token.
Okay. So this is so we cover right now what we have in terms of OpenMP for accelerators in 4.5 and the different clauses that we can use for mapping data structures, as well as specifying the parallelism and so on. However, there is also a new topic that we want to address in terms of OpenMP 5.0, and this is a topic that is relatively very new and is related to how are we going to do memory management in OpenMP in the case where we have architectures with different types of memories and so on. So at the beginning of this year, the OpenMP ARB put a technical report on memory management called TR5. And the idea of this report is to let know the community about how we want to be able to specify or manage different types of memories in OpenMP, as well as how will that how are we going to be able to control allocations to this type of memories and so on. This technical report is an ongoing process, and the idea is that from now, and it's one of a very strong candidates that we want to include in OpenMP 5. So right now we're in the design stages of this technical report, which one of the main concepts is that we are able to specify memory spaces and to specify memory resources that may be available on the different in a given architecture, as well as better ways on describing what are the memory traits for the different types of memory, and then where can we specify how in OpenMP we can allocate data structure to these memory spaces with these specific traits. And the idea is that with OpenMP we can define these memory spaces where we can characterize the memory spaces by different traits or attributes, and depending on that we should be able to define spaces and interface with the allocators, so that if we want to have a data structure to a specific type of memory, then we're going to be able to do that via OpenMP. One thing that is part of this TR is that it touches different aspects of OpenMP, and including the different ways we do data location and data sharing, and also device allocations, and also how we're querying for resources available the architecture, in the system. So this is a very important TR because it's kind of addressing all of these issues. Is going to help us to understand how we're going to really program these future architectures with complex memory hierarchies and different types of memories. And input is needed from you on these technical reports. And we want to provide a future webinar specifically on this memory management technical report because it's a topic on itself, and to start getting more input from applications so that we can start co-designing it so that by the time OpenMP 5, we can have a good draft that we can try to see we can add it to the specification, to the 5.0 specification, which is scheduled to be released by the end of 2018. So it's very important for you to be aware of it, and you should be able to access a very detailed explanation of the technical report through the OpenMP website, and there is a link to it, and you have to remember that this is work in progress, and comments from applications are very important, especially if we can come up with use cases that, to see if all the features are needed there, as well as what sort of functionality may be missing, and or are there any use cases for the data structures. And this is important. This is one of the most important features that we want to look in terms of in OpenMP 5. And yes, and we need your input. Part of the idea is that through the ECP project, we can connect better with applications and people like you. We are all part of the SOL project, Tom and I and other laboratories, members of laboratories with Barbara Chapman and as well as Bronis from Lawrence Livermore, where we would like to get more input about your applications, where you are in terms of implementing your code with OpenMP, and if you're going to use accelerators, how you're using it, and how do you plan to design your data structures and so on. And we want to really understand if we are meeting your needs, as well as what are the gaps and so on. OpenMP continues to grow in terms of adoption, as well as members that are supporting it. And we have, as I mentioned, a better release cycle in OpenMP, where via technical reports, where at the end, usually we have technical reports each year, and where we can have previews of what we see in OpenMP 5, as well as we have workshops where you can provide your input, as well as present papers and about your experience about OpenMP. We have the international workshop on OpenMP in Stony Brook, as well as OpenMP Con, which is basically a venue, an opportunity for you to present work or questions to the developers of OpenMP, and as well as a way to publish work or work in progress that you have in terms of porting applications using OpenMP. And the organization that manage OpenMP is the OpenMP Architecture Review Board, and if there is also interest for institutions to join, it's also possible to do that. There are different types of memberships and so on, but if you prefer basically to work closer with us, we can do it through the SOL project that we have in ECP, which we have a page in Confluence, and there we have like different milestones with different applications, and also surveys that we try to keep in in touch with applications and so on. I just want to mention this just so that you're aware that you have this resource available to you, where we can answer or set up webinars or ask specific technical questions that you can ask, and you can contact us. You can contact me or Tom or Barbara Chapman or who is the PI of the project. And with that, I just want to open the floor for questions and anything else that may come up with that you may have.
So at this time, since we're at the end of the webinar, I am going to go ahead and unmute everyone, and then that way everyone can have the ability to ask questions. You can still ask it in chat if you prefer. And so with that, 3, 2, 1, giving everyone the warning.
Okay. Ashley, this is Barbara Chapman speaking. This is not a question, but just to reiterate something that Oscar said.
How to close out. So I thought we prayed for proposal. Why don't you come with praise proposal?
Barbara, can you still hear us?
Oh, yes. I'm sorry. I thought I was hearing background. I thought nobody could hear me. Sorry. Just wanted to make the comment that it has a huge impact if people physically go to the OpenMP Con meeting and actually meet with the vendors and people implementing the standard. Several people have had huge successes that way in getting their engagement and really making a difference on their application codes. So.
Absolutely.
Well, I bring this up to get it started, I guess.
Ibrahim with Berkeley Lab. I have a question about the use of multiple devices. I understand that I can select one device and
hey, Mark, you want me to
offload.
If you're bringing it up, you pretty much saying I can get started before you present.
So about the use of multiple devices, I know that we can select one device and do the offload to it, but what about having multiple devices, and if we have some loops that we would like to split across multiple devices, or